So the Bohr model works pretty well for hydrogen, but it falls apart the instant things get more complicated. And it's pretty easy to see why. If you look at Bohr's postulates, the very first one is orbits are stable. And if you're talking about classical physics, that's clearly not true. Electrons are positive, protons are negative, so they're definitely going to be attracted to one another. If the electrons are spiraling around the nucleus, eventually they should be losing energy and they should eventually spiral into the nucleus. So right away, his first assumption, according to classical rules at least, doesn't work. And then if you look at the years just after Bohr's model was produced, it was found that just like how radiation can act like a wave, you can use wave physics to describe it, it was found that radiation also behaves like particles, right, with photons. And solid matter was found to behave like a wave sometimes and like a solid other times. So everything seems like it has these two sets of properties. And everything doesn't always behave like a wave or always behave like a particle. It kind of depends on the conditions that you're measuring things at and a number of different circumstances. But skipping just everything, Heisenberg proposed that this kind of wave-particle duality of matter meant that there's a fundamental uncertainty in knowing the position or momentum of an object. So that can be related mathematically as well. So this expression just says the change in x, so the change in position, multiplied by the change in momentum, which is just mass times velocity, is going to be always greater than or equal to this value h over 4 pi. And simplifying this a little bit, you get a proportionality. So the change in position is inversely proportional to the change in momentum. And simplifying it even further, you end up with this expression. And what this says is, as your mass decreases, the uncertainty in your x, your position, or your v, your velocity, gets larger. Or vice versa, as your mass increases, the uncertainty gets smaller. And this really doesn't matter for things that are very large, right? So if your mass is huge, the uncertainty in position and velocity is very small, right? So if you've got something like a house that weighs a ton, you're pretty confident as to where that house is, right? Its uncertainty in position is pretty small. Its uncertainty in velocity is very small. But if you go in the other direction, it becomes a big deal. So for an electron inside an atom, this has huge consequences because atoms have a tiny, tiny mass, right? So the mass is very small. The uncertainty in position and velocity gets much larger. So if you take a hydrogen atom, hydrogen is roughly 1 times 10 to the minus 10 meters in diameter. So if you use the mass of an electron and you work out the uncertainty in the position of that electron, you find that the uncertainty in the position of the electron is roughly 1 times 10 to the minus 9 meters. And that means your uncertainty in the position of the electron is about 10 times larger than the actual hydrogen atom itself. So you have no idea where that electron is.